Hello, everyone, and welcome back to another Math 104 lecture. So today what we are going to be discussing is the final math operation that we really haven't talked too much about yet. And that operation is going to be radicals or roots. So what we've discussed in the past is addition, subtraction, multiplication, division. Obviously, we've talked about fractions as well with complex fractions. Then we talked about absolute value and exponents. And now finally, we're going to discuss radicals and roots. And we're going to see some similarities between the radicals slash roots, whatever you want to call them, and exponents. And also, there's going to be a small tie-in of absolute value as well. Okay, so what is a radical? Well, the radical is actually going to be this piece right here, the little box-looking thing. That's going to be the radical. Inside the box is called the radicand. So that piece, that is the number of which the radical is applying the operation. And last but not least, there's also going to be this little piece here, which I'm going to circle. And technically right now I'm circling nothing, but you'll see why. That is called the index. Now, in general, when you don't see an index, when there's nothing there, when there's nothing there, that means that I pulled my screen super far down. Ignore that. When there's nothing there for the index, that means that the hiding number is actually secretly a 2, okay? But in general, we can see things like a cubic root, a fourth root, and so on and so forth. The index can be realistically any number. Okay, so just keep that in mind. But again, when it's not necessarily visible to you, it means square root. So what is a square root? What is this operation actually doing? Well, the purpose of this is it's basically telling you you have to try to find one particular number that when multiplied against itself, the number in the index, so in this case, twice. So I'm looking for a number that multiplies against itself twice that will give me 25. And you start thinking, oh, well, that should be pretty easy, right? That's just 5. And how do we know that this is the case? Well, that's because 5 times 5 is 25. And so now we realize that, okay, now we get it. 5 has to multiply against itself twice to give us 25, and that's what this square root is essentially telling us. Now, you also might realize, well, wait, there could also be a second answer here. And when we look at this, and you say 5 may not be the only answer, and the reason for that is there's also -5, right? And you say, well, yeah, because -5 times -5, the negatives are going to cancel, and it's just 5 times 5, which gives us 25. So technically, the square root of 25 will give us 2 answers. Now, I want to make this very clear. For the purpose of this class, unless you are solving for a variable, if you are solving for a variable, this doesn't apply. Ignore what I'm about to say. If you're solving for a variable, the rest of this is moot, okay? But if you are not solving for a variable, if I just present to you just square root of 49, for example, we are only caring about what is known as the principal square root. Principal means only the positive result, okay? So when you see principal, it starts with a P, think positive. Okay, so the principal root of the square root of 49 is 7, and only 7. We're neglecting the -7. Same thing here. The principal root of square root of 25 is only 5, not -5. Okay, so that is what I just crossed out is not the principal square root. And again, for the purpose of this class, unless I tell you otherwise, and unless you are solving for a variable, we are discussing principal square roots. Okay, so going forward, just keep that in mind. Okay, so there are some properties that go along with square roots. 2 of them are going to be pretty intuitive, and then one of them might take a little bit of explanation to get through, but we'll talk about it more. So here's the first 2. And the first one is if you have the square root of any 2 numbers that are being multiplied underneath that square root, you can actually split them up into their own individual roots. So that means if you have the square root of x times y, you can split it up into the square root of x times the square root of y. Okay, and that means that you can also, if you can go in this direction, the equal sign says that you can also go in that direction. So if you have 2 square roots being multiplied against each other, as long as the indices match, so remember this piece here, those numbers have to be the same. As long as those numbers are the same, and in this case they're both square roots, you can go ahead and combine them into one singular square root, and then the numbers just get multiplied. Okay, and similarly, the second property of them is this also works for division. So if you have one big square root of x over y, you can go ahead and you can apply the square root to both the numerator and the denominator separately as such. And again, just showing you if you can go in that direction, you can also go in that direction. So you can go backwards. And that's just saying that if you have the square root of some number in the numerator and the square root of some number in the denominator, as long as the indices match, and again, in this case, they're both square roots. Those are not sixes. I was trying to circle. I apologize. But they could be sixes. That's fine either way. Then that would just make that a 6. But not to confuse you guys. So as long as those indices match, you can go ahead and go backwards and make it one larger square root of the total fraction. Okay, so those are the first two properties. Now, before we get to the third property, I also want to make a note here. Remember, if we're talking about specifically principal square roots, we're talking about only the positive value that gets returned, right? Well, you might be asking yourself, okay, well, that's great for, limiting what the answer is, but is there any limit to what can go under a root? And the answer is actually yes. So if we have the square root of, and for right now, just for the purpose of this example, I just want to limit my scope to only square roots. We'll talk about cubic roots and fourth roots in just a second, okay? But for right now, square root. So say I have the square root of negative 49, right? Okay, so if I have the square root of negative 49 here, your first instinct might be, oh, well, it might just be 7. But then you say, well, wait a second, 7 times 7 is really just 49, not negative 49, right? So we're still missing that negative sign. And then you think, okay, well, what about negative 7? And you say, okay, well, negative 7 times negative 7. But remember, the negative signs are going to cancel out, right? Because when you multiply two negatives, you get a positive, and you still end up with 49. You might be asking yourself, well, wait, are we stuck here? Is there anything that we can do? And the answer is technically yes. And I alluded to this in a couple lectures ago where I said that very, very, very briefly, we would discuss complex numbers. If you have the square root or any even root, so that means if you have the square root, the fourth root, the sixth root, so on and so forth, if you have any even root of a negative number, you will get what is known as a complex number or an imaginary number. And I'm not going to dive too much into this, but an imaginary number is denoted as I, and we call that, or we basically assign it the value of the square root of -1. It is the base value, the base imaginary value. Okay, now that I would actually allow you to get an answer here. Your final answer of the square root of -49 is actually 7i. Okay, but don't worry about that. That's for future math classes. I just wanted to introduce to you the concept. If you are curious about this, if you want to know more about it, please feel free to come ask me. I'm very versed with complex numbers from my undergrad course. So, just let me know and I'll be more than happy to help you out with that. But for the purpose of this class, we don't really need to worry about that. All you need to know is that if you're talking about any even root, and you're talking about taking the root of a negative number, you cannot do it with only real numbers. It's not possible. You will get, basically, your final answer should be that there's no answer. There's nothing. You can't do anything. The square root of a negative number or the even root of a negative number will lead you to no answer in the real numbers. Okay, so just keep that in mind going forward. Now, just to elaborate a little more, say we had, I don't know, the cube root of -8. Now, realize here, the index is a 3, right? And 3 is odd. So this will not fall into what I was talking to you about before. Remember, you're only not going to get an answer if for the radical of a negative number if the index is even. When it's odd, however, you will get an answer, and we can show this, right? The answer to this is actually going to be -2. And why is that? Well, we're looking for a number that when multiplied against itself 3 times will give us -8. And we say, okay, well, -2 times -2 times -2. What happens? 2 of the negatives cancel out, but we still have 1 left over, right? So we know that we're going to get a negative number, and then it's just 2 times 2 times 2, which we know is 8. So again, you can see that this works out, and a negative answer, or an answer in general, is defined for taking the odd root of a negative number. Okay? All right. So now let's go ahead and discuss the final property of square roots before we get to any other examples. And that is this here. And we might run into a problem here, which I'll talk about in just a second. But you might say to yourself, oh, okay, well, this really shouldn't be too bad. If we have the square, so we have a number, it's being squared, but then we're taking the square root of it, right? So we're basically undoing it. Well, yes and no. The reason for that is because what you're doing is you're saying, I'm going to take any number in general, and it could be positive, it could be negative, and I'm going to square it. And what happens when you square any number? It's always going to be positive, right? And then when we take the square root of it, because we are only concerning ourselves with the principal value, we know that our answer will always be positive. So really, we're going to get the absolute value back of the original number. And let's look at a quick example just to really prove my point here. Say we have the square root of -3 squared. Well, we do the inside operation first, right? So -3 squared is just going to be -3 times -3, which the negatives cancel out, right? Because that's the whole point of the squaring it. And that's going to be equal to 9. And we square root 9. And because we're only concerning ourselves with the positive answer, we get 3 back. And now we see here x was -3. And our final answer was 3, so we took the absolute value of it. That's essentially what this process did. And what this allows us to do is this allows us to essentially give a new definition for absolute value. The absolute value of any number is essentially just squaring it and taking the square root of that number. Okay, so I hope that makes sense to you guys. And now just elaborating a little more on how exponents and radicals work together. If you have any let's say if you have any exponent, as long as you have the matching index, you can actually cancel these, right? Because if you're cubing a number and then you're looking for a number that multiplies against itself 3 times, that will give you the original number back, you're just going to get the original number, right? So if we say, again, we have 2 cubed and we have the cube root of it, well, you could go through the process of saying, okay, well, 2 cubed is 8, so we have 8 underneath, right? But then what's the cube root of 8? Well, again, we're looking for a number that multiplies against itself 3 times. That will give us 8, and that is just 2. So it's essentially the same thing as if you just canceled out the exponent with the radical itself. Okay, and again, going back to the property that we just discussed, it might work a little differently with even roots because you might get the absolute value back. But for most cases, you'll just get the number back. Okay, so not to confuse you guys, but one last example. If we have, and I'm just going to use 2 to the third one more time here. If we have 2 to the third and we have a 6 here, well, what do you think is going to happen? The idea here is that we can actually break the index up into its factors. So we can say this is going to be the same thing as 2 cubed. We're not touching the inside, but the index is really 3 times 2, right? And now what we can do is we can go ahead and cancel this with that, and we are just left with the square root of 2. Okay, so all we're doing is we're essentially canceling exponents with the radicals. That's how they work together. And by the end of this video, you'll have a little more insight as far as how that goes. But for right now, just trust me on that. Okay, so let's do some examples together and see how this actually works out. So let's say I tell you I want you to simplify the square root of 162. And you say to yourself, okay, well, that's a pretty big number. How do I approach this? One of the easiest ways to approach simplifying any number, as long as it's not a perfect square, which obviously feel free to check, but if we are going to check, and that should be the first thing that you check, you should say to yourself, okay, well, 12 squared, and I'll write this over here, 12 squared is 144, right? And so you say, okay, well, 144 is less than 162. It can't be 12. And then you say, okay, well, what about 13? And we say, okay, 13 squared, well, that's 169. And so if we take the square root of 169, we'll get 13 back. So clearly, the square root of 162 is going to lie somewhere between 12 and 13. Okay, so it is very much obvious at this point that it is not going to be a perfect square. So we have to do something else. Don't know if that canceled the video. Hopefully it didn't. We have to do something else to simplify this down. So what we can do is we can break 162 up into its factors. So we say, okay, well, 162 is an even number, which means that we can pull 2 out of it, right? So we say, okay, square root of 2 times, and what number times 2 is 162? Well, 81. And you say, oh, well, that's wonderful. 81 is a perfect square, right? 81 is 9 times 9, right? So that's exactly what we're looking for. And now we can apply the very first property that we talked about, and that is if we have two numbers being multiplied underneath a square root, we can separate them into each individual root. So we can say, okay, well, this is really the square root of 81 times the square root of 2. We really can't do anything with the square root of 2 anymore, right? Like that's done. That's a prime number that's underneath the square root. It has no other factors. We can't simplify it. So square root of 2 is just going to drop down. But the square root of 81, like we just discussed, it's a perfect square, and that's just going to give us 9, and that's our final answer. So when we're simplifying a larger number that has factors underneath a square root or any root, you're going to try to break it up into its factors such that one of its factors will be either a perfect square or a perfect cube or something that matches the index of what you're trying to accomplish here. So in this case, we were talking about a square root, right? So we were looking for a perfect square. If we had a cube root, we'd be looking for a factor that's a perfect cube. Okay? All right, let's look at our next example here. Say I want you to do the same thing. I want you to simplify the square root of 6y cubed, okay, times 12 square root of 12xy. Okay, now remember, whatever we did before with our first property with separating the square root, we can also return it, right? So if we have two roots of the same index, and in this case, both indices are 2, right? So it's the same thing. We can go ahead and merge them, and then we're just multiplying the contents of both. So let's go ahead and do that. And the reason that we're going to do that is because if you look at both of these, you say, oh, well, we can't really do anything with 6, right? There's really nothing to do there. And at first glance, you might say there's really nothing to do with 12. So, okay, let's multiply them together and see what we get. Well, to do that, what you're doing is you're essentially saying, okay, well, 6 times 12 and then times x, and then y cubed times y is the same thing as y to the 4th, right? All underneath the radical sign. And as a quick refresher, one more time, if you have the same base being multiplied, right, all you do is you add the exponents. So that's how we get y times y cubed gives us y to the 4th. Okay? All right. Well, now you could go through and you could multiply 6 times 12, and 6 times 12 is 72. And then you can go through the process that we did before of breaking 72 down into hopefully finding a perfect square, right? So that's one way to approach this. I'm going to approach this a little differently. What I'm going to do is I'm going to say, well, 12 is really the same thing as, so we brought down the first 6, but 12 is really the same thing as 6 times 2, right? And we keep the x, we keep the y to the 4th, right? And now we know that association with respect to real numbers will hold for multiplication, right? That's one of our properties. So we have the the commutative property, we have the distributive property, and we have the associative property, right? So the associative property just says, well, if I have 3 numbers that are being multiplied together, it doesn't matter in what order that I multiply them, right? So what I'm going to do is I'm just going to say, oh, well, this is really the same thing as 6 squared, right? It's 6 times 6 times 2. So it's really just 6 squared times 2, x, y to the 4th. And now what I'm going to start to do is I'm going to start moving things together that I want to separate from things that we know we can't do anything with, right? So we have a 6 squared underneath of the square root. We obviously know that that's going to cancel, right? Or you could think, oh, we have a 36, 6 times 6 is 36. That's obviously going to cancel with the square root. So either way, however you want to think about it, I'm just going to keep it as 6 squared just for simplicity's sake. So we keep it as 6 squared here. And off to the right, I'm going to write my 2 and my x. And the reason that I do that is because there's nothing that I can do with them, right? I only have one x. I only have a singular 2. Neither of them are, squares that I can do anything with. But the y to the 4th, however, now that is absolutely something that I can do something with, right? That is an even power, and we have an even index. So what I'm going to be doing is essentially I'm going to break this up into their two different parts like I did before. So we have 6 squared, y to the 4th under 1. And then under the other, we have the 2x. And notice what I did was I separated them by things that I knew would cancel and things that I knew would not cancel. So the things that would not cancel are off in their own box. They're not going to do anything anymore. That's essentially their final form that we're going to be bringing down with each step, right? So what happens? Well, we know that when we take the square root of 6 squared, the squares are going to cancel, right? And when we take the square root of y to the 4th, again, what you're thinking of is two numbers that multiply together to give you y to the 4th, right? So if I'm thinking of two numbers that multiply together to give me y to the 4th, this is really the same thing as y squared times y squared, right? So our answer when we take the square root of y to the 4th is y squared. So we do this and we get 6y squared times the square root of 2x, and that is our final solution. That's it. Okay, so at this point, I want to give you guys an opportunity to go ahead and try your hand at the first classwork assignment. The first classwork assignment is the square root of 20y cubed all over 27x squared. Okay, so go ahead, give this a shot, see what you come up with, unpause the video whenever you are ready. Okay. Again, I'm including that just for future classes if you decide to come back and look at this. That's some jargon that you'll need to know later for as far as domain is concerned. But right now, you can kind of ignore the x is not equal to 0 and the y is greater than equal to 0. But again, it should follow in line with what we've discussed before, right? If x is 0, then you get a 0 in the denominator, the fraction blows up. And if you have y is less than 0, then you have a negative number underneath the square root. And we already discussed what happens. If you have a negative number in a square root, then obviously you won't be able to get an answer. It'll blow up. Okay, so hopefully you guys gave it a shot. Let's go ahead and work at this together. Now, what we have here is the square root of a fraction, right? But remember, what we can do is we can apply that square root to each individual piece. We can apply it to the numerator and also the denominator. So that's exactly what I'm going to do. We're going to say, okay, well, this is the same thing as 20y cubed all over square root of 27x squared. Okay, why don't we work with the denominator first, because we have an x squared, and intuitively that might be easier to understand, right? So I'm just going to keep the numerator the same, and we'll work with the steps out later for that. So 20y cubed all under the square root. Now, for the 27x squared, we obviously know x squared is going to cancel with the square root, right? That's the whole point. But 27, what are we going to do with that? Well, the idea here is when we have a number that's not a perfect square and we know that it has factors, we want to break it up into its factors such that one of them is hopefully a square root in this case, right? Or I'm sorry, a perfect square in this case, because we have a square root. So we want it to cancel with the square root. We want one of the factors to do that. So we think, okay, well, what are factors of 27? And we come up with, oh, 3 and 9, right? And that's perfect because 9 is a perfect square. So we say, okay, so we have x squared times 9 times 3, right? And just for simplicity's sake, I'm just going to bring everything down. So we have square root of 20y cubed up top. And we know that what's going to happen here is when we take the square root of x squared, we get the absolute value of x, right? We don't know what x is, but we know that it's going to be positive, right? Because the square is going to make it positive, and then when we take the square root of it, we're only talking about that principal value, right? So we get the absolute value of x. And if you were trying this and you only happen to get x, it's not the biggest error. Just keep it in mind that your answer will always be positive for x, okay? So we get the absolute value of x, and when we take the square root of 9, we know that we're going to get 3, right? And I'm just going to put that in front. It doesn't matter. You can put it in behind. And then finally, square root of 3, right? We can't do anything else with it. And visually, if you wanted to, if it made more sense doing it in one more step, what you could have done is, and again, just keeping all this the same up there, what you could have done is you could have split this up into the two boxes like we tried doing before, where you say, okay, well, 9 is going to cancel, right? X squared we know is going to cancel, but 3 is not going to cancel. So we know that the square root of 3 is just going to, come down with us. Okay, So the denominator is taken care of. Let's talk about the numerator. So as far as the numerator is concerned, we're going to do the same exact thing to the 20, right? We're going to look at the factors of it such that one of the factors, at least one of the factors, will be a perfect square. So you might off the bat think, okay, well, 2 and 10, but is that really going to help us out? And the answer is no, right? Because 10 is not a perfect square, 2 is not a perfect square. So even if we separate it out into those factors, that's not going to work. However, 4 and 5 will definitely work because 4 is a perfect square. And that's what we're looking for here, right? So we say, okay, well, we have the square root of 4 times 5. And now you say to yourself, well, what about the y cubed? Now, obviously, y cubed is not an even exponent. So it's not going to cancel perfectly. But there is a y squared hiding in there, right? And off to the side, y cubed is really the same thing as y times y squared, right? We're just breaking it up into its factors. And you could obviously go back and check this because how do you multiply numbers of the same base with different exponents? You just add them, right? And what's the hiding exponent here? A 1. So we know that this works either way. Y cubed is the same thing as y times y squared. We're just breaking it up into its components. And that's what I want to do because I want to focus on this piece here, the y squared. So we say, okay, well, y squared times y, and we already figured out the denominator, and that was 3 times the absolute value of x times square root of 3. And now what I'm going to do is the same process that I did before, right? I'm just going to separate things into their each individual boxes. Don't feel like you absolutely need to do this step. This is just, technically helpful if you need to see it conceptually. So what I do is the first box is all the stuff that can cancel. So we know that that's going to be the 4. We know we have the y squared in there as well. And then the second box is all the stuff that's not going to cancel, right? So we have the 5, we have the y, and all over our denominator. And last step here is to just go ahead and figure out what's going to happen. So we know here that the square root of 4 is going to give us 2. The square root of y squared technically would give us absolute value of y, but we already know, going way, 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 way back up here, this piece here, right? Y is greater than or equal to 0. So we already know that y is positive. So I'm going to just forego that absolute value and just say 2y. If you did put the absolute value of y, totally correct. That's absolutely fine. It was just one of the things that I'd given you up top, let you know that it was already positive. So 2y, and we know that nothing else is happening to this square root of 5y, right? So that's done. All over 3 times the absolute value of x times the square root of 3. And this is your final answer. You are finally done with simplifying this monster over here that we started with. Okay? So hopefully that makes sense to you guys. All right, let's go ahead and clear this off and continue. So now we have to consider how do we multiply radicals when the indexes are different. So let's look at an example. Say I have the square root of 2 times the cube root of 5. Now, this might not make immediate sense to you until you consider what we do with fractions. What do we do with fractions when we have to, add or subtract fractions? We have to kind of manipulate them, right? We have to change the denominator, and then to change the denominator without changing the value, we also have to change the numerator, right? We're going to go through a very similar process, but in this case, we're just talking about exponents, right? There's no numerator, there's no denominator that we have to mess with. The idea, the principle, though, is still there. We're changing something without changing its value. We're just going to change its appearance. So we know that the square root of 2 is, and again, the hiding index here is a 2, right? And that's important to keep in mind. So let's just look at this one piece at a time. The goal here is we have to get the square root of 2 and the square root of 3 to match. So what I'm going to do is, again, one piece at a time. I'm going to take my square root of 2, and I'm going to say, okay, well, I'm going to cube the inside, because whatever I do to the inside, whatever I do to the radicand, I also have to do to the index. So we had a 2 out here, right? Now, because I raised my radicand to the 3rd power, I also have to raise my my index to the 3rd power. So 3 times 2 for the index, and we know that that's just going to give us 6 out here. So the square root of 2 is technically equivalent to the 6th root of 2 cubed. Okay? So again, all I did was I raised the inside and I raised the outside. Whatever I do to the inside, I also have to do to the outside, okay? And that's just in terms of exponents. Now I'm going to do the same thing to the cube root of 5. And the reason is, again, we're hoping to get a 6th root, right? If we can get a 6th root here, then we can finally do our multiplication because the indexes will match. So we're talking about the cube root of 5 here. And again, what I'm going to do is I'm going to multiply the outside by 2 because I'm hoping to get a 6. But whatever I do to the outside, I also have to do to the inside, all right? So I'm going to raise 5 to the 2nd power. And now what this gives me is I now get the 6th root of 25 and the 6th root of 8. Okay, hope you guys are still with me with that. And now that we have our following indexes and everything matches, we can then say, oh, well, this is really just equivalent to the 6th root of 8 times the 6th root of 25. And now because the indexes match, we can combine them as one larger radical. So we have 8 times 25. And 8 times 25, if you don't know it off the top of your head, you can think about it as 4 times 25 times 2, which is generally how I think about it, and that is just 200. So, and of course, feel free to use the calculator to double check me, but we get the 6th root of 200, and this is going to be your final answer. And this is your final answer because, again, all I was asking you to do was just multiply the two different radicals that had different indexes. Okay? All right. So next topic here is called rationalizing radicals. So what does that mean? Well, rationalizing is where we have a radical in either the numerator or the denominator, or possibly both, and the directions specifically indicate that you have to rationalize either the numerator or the denominator. And the process of rationalizing basically just means we don't want the root in there anymore. We're trying to get rid of that radical sign. So let's look at an example and that it'll be a little more clear to you. If we have the square root of 3 over the square root of 8, and I say I want you to rationalize the numerator, okay? And I'm going to write numerator just so no one forgets. So we're trying to rationalize the numerator. That means that what I want to do is I want to get rid of the square root of 3 up top. I don't want that square root anymore, okay? Now again, this process, much like a lot of the things that we've done before, involves changing the appearance without changing the total value. Now, to get rid of a square root, you might think, oh, well, we should just square it, right? And you'd be on the right track, but if we square it, we're changing the value. We're inherently changing the value, right? Because we're also squaring the denominator. So that's not going to work. We can't just inherently square that. But what is the process of squaring? Squaring is saying we're going to take one number and multiply it against itself, right? And because we're trying to rationalize the numerator, that's exactly what we're going to do. We're going to say, oh, we have a square root of 3 up top, so I'm going to multiply it by a square root of 3. The trick is, though, whatever we do to the top, we also have to do to the bottom, right? Again, square root of 3 over square root of 3 is the same thing as multiplying by 1. We're just doing it cleverly so that it changes the value, right? And now square root of 3 times square root of 3, you can either think about it as combining the square roots, and that's 3 times 3, which is 9, and then take the square root of 9, which just gives you back 3. Or you could say it's a square root of 3 squared, and then obviously the exponent and the square root would cancel. You just end up with 3 either way. And then down below, we get the square root of 8 times the square root of 3. You get the square root of 24. And technically, yes, you could go ahead and simplify this a little bit more. And you say, okay, square root of 24, that's going to be the square root of 4 times 6. And that's just going to give you 3 over 2 square root of 6. Now that simplification, the final two steps indicated by arrows here, these final two steps aren't necessarily the goal of this. The goal here is that you understand what rationalizing is doing. Again, our goal was to rationalize the numerator. So what we did was we saw that there was a square root in the numerator. We multiplied it against itself, so it squared the square root. It got rid of it. And we ended up with just a regular integer up in the numerator. Now, this is a very important thing to keep in mind. You can never fully get rid of the square roots. if you have a square root in both the numerator and the denominator. If I say rationalize the numerator, notice we still ended up with a square root in the denominator. You can never, even if we were to do it the other way, even if I said rationalize the denominator in this fraction, you would still end up with a square root in the numerator, okay? So don't think that you're doing something wrong just because you end up with a square root in your answer, as long as that square root is not in the part of the directions. So again, the directions said numerator, there's no square root in the numerator, you're basically good. Okay? All right. Let's look at one more example as far as rationalizing is concerned. And this is not going to be square roots. We're going to talk about cube roots here. So let's say we have the cube root of 4 over the cube root of 9. Now, our process here is going to be slightly different. And the reason is before we recognized, okay, we had a square root. So if we squared the square root, that was our original goal, then we could cancel it, right? Well, we can't really do that here, right? If we square the cube root, the square and the cube root aren't going to cancel, right? The numbers don't match. The exponent does not match the index of the radical. So nothing's going to cancel if we do that. So our goal here is, and again, I should have specified, sorry, our goal here is to rationalize the denominator. Don't know if I said it, but I will write it again. We're trying to rationalize the denominator here. Okay, so our plan of attack here is we say, okay, we have a cube root. What I want to do is I want to multiply 9 such that I get a cube root inside of the radical. Because if I get a perfect cube inside of the radical, then it'll cancel with that cube root, right? So you think to yourself, okay, well, what are some cubes that are pretty close to 9? And you say, okay, well, 1 cubed, and feel free to write it out if it makes more sense to you. 1 cubed is 1, right? 1 to any power is 1. 2 cubed, we know from experience, is 8. And then you say, okay, well, what about 3 cubed? Well, 3 cubed is 3 times 3 times 3, which is 9 times 3, which is 27. And you say, oh, yeah, 27, this might work because 9 goes into 27, right? So I'm just going to erase this for the purpose of room. And you say, okay, well, now we have a plan. I want to make my 9, I want to make my cube root of 9 into the cube root of 27, because that way things will cancel in the denominator and I won't have the cube root anymore. So what we're going to do is we're going to, in the denominator, multiply by the cube root of 3, right? Because what we can do here is we can combine them, and then we can multiply the 9 times 3. We get the 27 like we wanted, and we're good, right? But remember, whatever we do to the denominator, we also have to do to the numerator, right? So what do we end up getting? Well, we get the cube root of 4 times 3 up top. We get the cube root of 27 up in the bottom, right? Because 3 times 9 is 27. And last step is just to simplify. We get the cube root of 12 up top, all over. The cube root of 27 is just 3, and voila, we have now rationalized the denominator because we just have a regular number, no more root in the denominator. Okay, so our plan of attack was a little different, but still the same idea, right? Rationalizing just means we're trying to get rid of the root through whatever means possible. Okay, and now what happens if we have more than one term inside, the numerator or the denominator? Well, for that, you're going to have to be familiar with a term called conjugates, or a conjugate pair. And what is a conjugate pair? A conjugate pair is anything in the form of a square root of x minus b square root of y and a square root of x plus b square root of y. And don't get too bogged down in the variables. All this is basically saying is you have two different terms that are possibly, square roots, and they each have their own coefficients. Okay, so that's really just what it means. Now, the important part here is that you notice there's a minus here and a plus here. Conjugate pairs are always going to have flipped signs. And we're going to get right back into the thing that I've been trying to drill into you guys for a while now, which is difference of squares. Difference of squares, difference of squares, difference of squares, right? When we have something, we have two different terms, right? And say we multiplied them. If they're the same two terms being multiplied, but just different signs, we're going to get a squared minus b squared, right? And we're going to see this come up here, and that's going to be our plan of attack. So let's look at an example, because it'll make more sense with an example. If we have 2 square root of 5 minus square root of 10, and this is all over 2, and I say I want you to rationalize the numerator, obviously, right? Because the denominator is already rationalized. So when I say rationalize the numerator, and you say, well, I have no idea what to do, because if I multiply by just square root of 5, for example, square root of 5 times square root of 5, sure, that square root of 5, when I distribute it over here, is going to make things better, but when I distribute it over here, it's going to make things substantially worse, right? We're going to get the square root of 50, and we're still going to end up with a square root. So that's not going to help us. And similarly, the same problem is going to happen if you try multiplying by the square root of 10, right? So that's not really going to help us. But what is important to take away here is we have a conjugate, right, in the form of something minus something, right? So what we need to multiply by is the exact same thing, but just the different sign. So we have 2 square root of 5 minus square root of 10. Our plan of attack here is we're going to say, okay, well, we're going to multiply by 2 square root of 5 plus square root of 10. And remember, whatever we do to the top, we also have to do to the bottom. So 2 square root of 5 plus square root of 10. And now what is this going to do for us? What does this actually do? Well, when we multiply fractions, right, we multiply across, right? So I'm just going to kind of do us a favor. And before I get to any other steps, I'm just going to rewrite this as one singular fraction. So we're going to say, okay, we have 2 square root of 5 minus square root of 10 times 2 square root of 5 plus square root of 10. And this is all over 2 times 2 square root of 5 plus square root of 10. Okay, it looks a little beefy. It looks kind of hard to deal with, but it really isn't, because what do we have? Well, it looks a lot like difference of squares, right? We have 2 square root of 5, and that's going to be my a term, right? So we have a minus b, right? Where square root of 10 is my b. And then we also have that same 2 terms, but just added, right? So a plus b. And what does the difference of squares give us? Well, it gives us a squared minus b squared. So what do we really have to do here for the numerator? All we really have to do is just square the 2 different terms and then throw a subtraction sign in the middle, and the numerator is done. So our first term is our a is the 2 square root of 5, right? So 2 square root of 5 squared, 2 square root of 5 squared minus, and then our second term, square root of 10, also squared, and then all over our denominator, which I'm not going to distribute the 2, and you guys will see why in just a second here. If you did distribute the 2, that's totally okay, but you'll see why. So 2 times 2 square root of 5 plus square root of 10. Call it intuition, whatever you want to call it. So now what happens to our numerator? Well, when we do the exponent, we just distribute the exponent to each individual piece, right? So we get 2 squared, which is 4, and then times, what is a square root of 5 squared? Well, the square is just going to cancel with the radical sign there, right? So 4 times 5. And we get a minus. And finally, we get the square root of 10 squared, which, again, things are just going to cancel there, right? The square root is going to cancel with the exponent. So minus 10 all over 2 times 2 square root of 5 plus 10. And 4 times 5 is 20. 20 minus 10 is just going to give us 10 all over 2 times 2 square root of 5 plus, that should have been square root of 10. My mistake. Glad I caught that. Square root of 10, square root of 10. I didn't make that mistake anywhere else, right? No. Okay. Cool. Okay, and the reason that I didn't distribute this is because we essentially have a 10 divided by 2 situation, so we can just go ahead and cancel the 2 out with the 10, and we get a 5 up top, and now our final answer is just going to be 5 all over 2 square root of 5 plus square root of 10, and that is your final answer. So what is really the heart of this, of this procedure? The heart of this is essentially just saying, okay, well, we have 2 different terms, but we have a minus b. So if we multiply it by a plus b, we get the difference of squares situation. And obviously identifying that, what each term might be a little confusing, but it's your first term is whatever is in front of the subtraction. So the whole thing, right? It's because it's being multiplied 2 times square root of 5. That's your whole first term. And then your entire second term is whatever is behind the subtraction sign, right? And so we keep those terms the same, and we just add the addition sign instead of the subtraction sign, so that way we can actually get a difference of squares situation. Okay, so with all of that being said, why don't you go ahead and try your hand at the second classwork assignment, which is x minus 2 all over the square root of x plus the square root of 2. And again, your goal here is to rationalize the denominator, okay? So rationalize the denominator. We have two different terms in the denominator, so you're going to have to probably try the same method. So give it a shot, unpause the video when you are ready. Okay, so hopefully it wasn't too bad for you guys. So our first term, our a term, if you will, is square root of x, right? We have an a plus b situation. Before, in the last example that we did together, we had a minus b to start with. So we had to multiply by the conjugate pair, which was a plus b. This time we're starting with the addition, so we have to multiply by the subtraction version of it, right? So we're going to keep the terms the same, square root of x, square root of 2, but we're going to flip the sign. We're going to say minus in between. And whatever we do to the bottom, we also have to do to the top, right? So square root of x minus square root of 2. Now, again, what I'm going to do is I'm going to, just for the purpose of really articulating this, I'm going to make it one fraction. If you guys already see the pattern, feel free to just skip this step. You don't necessarily have to write this out, but I'm just writing it out as one fraction for everybody who, still might not see it. So we have x minus 2 up top times square root of x minus square root of 2 all over square root of x plus square root of 2 times the square root of x minus the square root of 2. And again, what do we see here? Well, we have our goal, right? We have an a plus b times the same two terms, right? A minus b. So this should give us a squared minus b squared. So in this case, what it's going to be, our a is the square root of x. So we get the square root of x squared minus, right, because that's the integral part of the difference of squares, minus the square root of 2 squared, because square root of 2 was our b term, right? And then we just keep the numerator the same, where we had x minus 2 times the square root of x minus the square root of 2, okay? And we can go ahead and simplify this because we know what's going to happen to our denominator. Our square root of x squared, well, this is going to purposely cancel, just like we had planned, just like the square and that square root there. So what we get is x minus 2 in the denominator, and we have an x minus 2 up here times square root of x minus square root of 2. And if you stopped here, I might take 1 point, maybe half a point off, because technically there is one last step that you can do, and this goes back to the very last lecture that we did, the one previous to this one, which is rational expressions, right? If you have the same polynomial expression in the top as you do in the bottom, what can you do? You can go ahead and cancel them, right? So we have an x minus 2 up here, we have an x minus 2 up here, which means we can cancel it, and our final answer is just going to be square root of x minus square root of 2, which is this piece here that was left behind. Okay, so hopefully all that makes sense and that wasn't too bad for you. I want to try to speed through this last topic just because I know I'm running short of time, and this video is probably going to be a little longer than I'd like, but it's pretty important, and I said that things would, as far as exponents and radicals, would make a little more sense by the end of this video, and that's the next topic that we're going to talk about. So the last topic that we're talking about here are called rational exponents. So before I even define this, you should think, okay, well, what's a rational number? A rational number is just a fraction, right? It's just anything in the form of a over b. And we had that other word in there, exponents, right? So essentially, it's just where you have a fraction as your exponent. So you have x to the a over b. And of course, there's that normal jargon where b cannot equal 0, because if you have b is equal to 0, then you get a 0 in the denominator. The world blows up, game over, right? And we don't want that. So that is obviously our biggest constraint there. Okay, now what is a rational exponent? What does this actually mean when we have x to the fraction? What is a fraction? Well, let's look at a basic example. Let's say we have x to the 1 over n, right? So we don't necessarily know what n is, but we can say this is actually going to be the same thing as if we take the root of x, where n is our index. And that is how these two equate. We've already talked about what a negative exponent means. A negative exponent implies that your answer is going to be some sort of fraction, right? It's going to flip your answer, right? If I had a x to the -1, then we know that this is the same thing as 1 over x, right? Well, it's the same idea here, except the fraction implies that we're going to have some kind of root. And the number in your denominator is going to directly correspond to your index. And they can go back and forth, which means that you can go freely from the radical form to the rational exponent form. These are both equivalent and they mean the exact same thing. Okay, so what does this actually mean? Let's look at our previous example that we did before. Say I have the 160 to the 1/2 power. Okay, so 160 to the 1/2 power, well, this is really just the same thing as if I take the root of 160, and then our denominator comes way over here and becomes our index, and that just means that we have a square root, right? Because the 2 is our index, and if 2 is our index, I'm just going to leave it out. I'll write it in red, that's fine. But it just means that we have a square root. So we have the square root of 160. And now what we do is just the same normal procedure that we did before. We look at the factors of 160 and see how we break this up. And we say, okay, 160, we're looking for a factor of this that is a perfect square. And we say, oh, well, 160 is divisible by 10. So this is really the same thing as 10 times something. Well, 10 times what gives me 160? Oh, 16. And that's perfect because 16 is a perfect square, which is exactly what we were looking for. And then we can simplify this by splitting them into their own individual boxes, right? Square root of 16 times the square root of 10. And then we know that we get 4 times the square root of 10. And that's your answer. So you see, we started with a rational exponent, and then we converted it to a radical because it was a little easier to understand in that way. But they mean the exact same thing, and hence we can then say, obviously, that these are equivalent. So 160 to the 1/2 power is the same thing as 4 times the square root of 10. Okay, so that is your first example. Now, what happens if our numerator of the rational expression, of the rational exponent, sorry, so this piece here, what happens if that is not 1? Well, we actually kind of know this. If the exponent is 1 there, then the exponent is 1 here. And sorry, that was supposed to be a 1. I just wrote over it many times. So the exponent in the numerator is going to directly correspond to the exponent of your radicand. So let's look at an example of that. Say we have, and I believe this was an example on your preliminary exam, say we have 8 to the 2/3 power. Well, 8 to the 2/3 power, this is just going to be the same thing as, okay, we put a root sign, right? Because we have a fraction, right? And the fraction implies that we're going to have some kind of root. We take our 8, we stick it in here. Now, remember, the 3 corresponds to the index, so this is a cube root. But the 2 here is going to correspond to 8 squared. So it's not just 8, it's 8 squared. And now what we can do here is we can say, okay, well, what is 8 squared? 8 squared is 64, right? So we have the cube root of 64, and we say, okay, what's the cube root of 64? We're looking for a number that when multiplied against itself 3 times will give us 64. And you say, okay, sure, you can go through them again. We already, from last time, we picked up at, we know 3 cubed is 27, right? Well, what's the next one? 4 cubed is the same thing as 4 times 4 times 4, which is 16 times 4, which is 64. And hey, that's exactly what we wanted, right? So that means that the cube root of 64 is just 4. So that means that we can say 8 to the 2/3 power is 4. And now you might be wondering, okay, well, is there a method to, like, do we have to do this in a particular order? Can we do the root first and then the exponent? And the answer is yes. These are actually equivalent. So if we do the other order, right, and we do, okay, well, let's say 8 to the 2/3, but now we flip the order and we say, okay, we're going to do the cube root of 8 first, and then we're going to square it. Okay, well, that's totally fine. What's the cube root of 8? Well, that's 2, right? So we get 2 squared, and we see that it's still equal to 4. So in general, if we have anything in the form of a to the m over n, it's going to be the same thing as the nth root of a to the m, or the nth root of a to the m power. So it doesn't necessarily matter which order you do it in. Now, as far as convenience is concerned, there will be times where it is far more convenient to do this one over this one, or it might be more convenient to do this one first and then that one. So it really just depends on your situation, but just know that they are equivalent. Okay, so let's work through one more example here, and then I'm going to let you guys do the last classwork assignment, and that's going to be it for today. So let's say we have 4x to the 1/2 power times 3x to the 1/5 power. And I should also mention here, before we actually get to this, all of the properties that apply to regular exponents, so say we had x squared or x cubed or whatever, all the properties that apply to exponents that are integers also apply to rational exponents. So that means that if you had, again, we're going to go through this, if you had x times x, right, what do? You add up the exponents, right? They're both 1, and that means you get x squared, right? Well, the same thing applies if you have x to the 1/2 times x to the 1/2. All you're going to do is you're still just going to add the exponents. So you get x to the first, which is just x. Okay, so all the same properties that apply to regular exponents apply to rational exponents. And if you need a refresher, go back into the previous lecture and check out those properties just so you can stay up to date. Okay, so what's our plan of attack here? Well, the 1/2 power is only applied to the x, not to the 4. And the reason that you know that is because there's no parentheses around this, right? If there were parentheses around this, then the 1/2 power would also be applied to the 4, and this would be a different story. But that is not the case. Same thing with the 1/5, right? There's no parentheses around the 3x, so the 1/5 power is just being applied to the x. So what are we going to do? Well, we're just going to multiply the things that we know that we can multiply. So 4 times 3 go together, and then x to the 1/2 power times x to the 1/5 power. And we say, okay, well, the easy part, 4 times 3, that's going to give us 12. And then we say, okay, well, what's our process here? When we have a base to an exponent multiplied by the same base to a different exponent, we just add them, right? So all we're doing is essentially we're going to keep the base the same, and we have 1/2 plus 1/5 for our exponent. And this is where your fundamentals come in as far as changing fractions to match each other so that way you can add them. So this is really just going to be 12 times x to the 5/10 plus 2/10, which gives us our final answer of 12x to the 7/10 power. And this is going to be your final solution. Now, if you wanted to, be super technical about it, if I said also that I wanted you to convert it back to a radical, you can do that too, right? And the way that you do that is you keep the 12, right? Because 12 has nothing to do with the exponent. So we keep the 12 out. And then remember, the fractional exponent implies a root. So we're going to have some kind of root. X is our base. And then it's up to you however you want to write it. If you want to write the numerator inside, then you can totally do that. So then x to the 7th, and then the 10 correlates to our index. So it's the 10th root of x to the 7th power. Or again, as we discussed, this is the same thing as 12, and then you can put the exponent on the outside. So the 10th root of x to the 7th power. Either way, totally fine. And you would only need to write these two if I say convert it to a radical. But because that was not the case, I didn't say that in the directions, then you did not need to write it that way. It was just a little more review, so that way you could understand. All right, so last classwork assignment, and then we'll call it a wrap. We have factor x, I'm still in red, sorry. So we have factor x to the 1/2 minus x to the 5/2. So go ahead, try your hand at this. It's not going to be intuitive. So see if you guys can figure it out and then come back. Remember, we're trying to factor. Okay, so hopefully you guys gave it a shot and it wasn't too bad. So what are we trying to do here when we're trying to factor? The idea is when we're trying to factor, if you're talking about the previous lessons, we're trying to look for something that's in common between both of them, right? Something that we can say, okay, we can pull this out of both of them, and that way we'll have something left over, right? Okay, so we look at both pairs and we say, okay, well, obviously there's an x, in both. So we know that we're going to pull out some power of x, and that means we're going to have something left over. Now we have x to the 1/2 in the first position, and then we have x to the 5/2 in the second position. Well, we can rewrite this. This is really the same thing as x to the 1/2 minus x to the 1/2 times 5, right? So all I did was I just brought the 5 out of the numerator. And now this might actually seem a little more apparent, right? Let's say just hypothetically, there was no 5 there. Well, you guys could definitely answer this, right? You could pull x to the 1/2 out of both, right? And then if you did pull x to the 1/2 out of both, then you just get a 1 minus 1 situation, x to the 1/2 times 0, and that's it, right? And then you'd basically be done. But we do have that 5 there, and that 5 is kind of a problem, right? But that doesn't mean that our process is any different. We now recognize that there's an x to the 1/2 in both of the terms. So what I'm going to pull out is x to the 1/2. And when I do that, when I pull x to the 1/2 out of the first term, well, that was the only quantity of x that was there, right? So x to the 1/2 divided by x to the 1/2 just leaves me with 1. And now if I pull out x to the 1/2 out of x to the 5/2, you can think about it as this. And what do? Again, the process when we have the same base of being divided, we just subtract the exponents, right? So we have x 5/2 minus 1/2. And that just leaves us with x to the 4/2, which is just x squared, right? So if I pulled out x to the 1/2 from both pieces, we end up with a 1 minus x squared. And you say, great, we're done. And then I would probably take like a point or two off because you're absolutely not done. Remember, the entire goal of this is to factor, right? And what do we have? Well, what is hiding here for the exponent of 1? The exponent of 1 could be any exponent, right? Because 1 to any exponent is still just 1. So why don't we just make it a squared? And we say, oh, we have a square, we have another square. So we have a square here, we have a square here, and we have a difference. This is a difference of squares, right? So we're going to keep the x to the 1/2 out. And to factor difference of squares, we get a plus b times a minus b, right? What is my a? My a in this case is going to be 1 plus x, and then 1 minus x. And now we are done. And that is it. Okay, so give a shot at the homework. Hopefully it makes sense. I know this was a pretty long video. I apologize. I'm still trying to figure out, the exact length of these videos. I know I told you guys I wanted it to be about 50 minutes, so I'm finding my way. But just bear with me, and hopefully it'll get shorter as we go along. The preliminary chapters, by the third edition, they're called the P chapters. They're generally longer than almost all the other ones. So hopefully, because this is the last P chapter, we're getting into all the the actual new material from this point on. Material that I hope you haven't seen yet, and if you have, you definitely haven't seen all of it. So those chapters should, in theory, be shorter, which means the videos should also be shorter. Okay, so as always, feel free to reach out to me if you've had any problems with the homework or with understanding the lecture. Please let me know if you're having those problems, and you can come talk to me during office hours. Anyway, enjoy the rest of your day or night, and I hope you all stay safe and healthy. All right, see you guys.